Okay. Hello everyone. Welcome to week 3. This week we're going to learn how to turn instructions into machine code. So, okay. Instructions are encoded in 32 bits. Okay, so if you remember your ARM instructions, those actually decompose into 32 bits, and we usually write them in terms of hex um, uh, in order to represent them, say, in a compact manner. So, for example, you have hex. Each character of this actually turns into 4 bits. So, um, since you have these, you can turn it immediately into the binary representation. So whenever you see instructions, you can write machine code directly in hex form in order to make it at least somewhat human, somewhat easier to see. It's still not very human readable, but it's somewhat easy to see when you put it in hex form. Okay, so example. Data processing instructions. What are data processing instructions? It's the instructions of the type add, sub, and the shift instructions. Set if less than and stuff like that. Those are logic instructions. These instructions are called data processing instructions, and they are structured as written here. Okay, so what's condition? Condition is basically, you may have seen it in the instructions lectures. Condition is usually 1101 if always. So for example, if you have the add instruction, there's an implied condition here that's always true, which is 1101. There are other conditions. You can consult the ARM ISA, the ARM instruction set document from last week, in order to see all the conditions. It's somewhere in there. But basically, you have add LT, add if greater than, add if equal. So basically, these are things that depend on the previous instructions status registers. So these parse the XPSR in order to see whether or not these instructions should actually go ahead and be executed. So these words right here are actually what you put into the condition. So just remember that if it's always true, it's 1101. But you're gonna have to consult um, the the manual from week 2 in order to see which conditions are which. Opcode. So opcode is actually the one that okay, let's switch here. So this is 1101 if always, and something else if not. So actually if equal, if I remember correctly, that's 000. So yeah, condition varies depending on this part of your instruction. Opcode is the one that decides between the 3 types of instructions. So you can see up here, if opcode is 00, that means it's a data processing instruction. So let's assume opcode is 00 for now. We're going to change the opcode later. Funct. Okay, funct is something that's specific. So this thing is actually the one that separates between all the data processing instructions. So whether or not it's a shift, whether or not it's add, sub, or those differences are in funct. Okay, RN and RD. Basically, for your instructions, you have this type of format. So RD is actually that one, and RN is actually that one. So for these instructions, you are guaranteed to have at least one register operand. So that guaranteed register operand is going to be RN, which is always placed here. What about RM? Well, the thing with RM is you're actually not sure if it's there, because sometimes you can have immediates as input to the add instruction. So that's why we have source2. So source2 is something that varies. So you can see that in this next slide. Okay, so let's break it down. Let's come back to source2 later. Okay, so we have here condition. Okay, so condition of code already discussed. Now funct is actually broken down into I, CMD, and S. So CMD is something that is specific for your instruction. So say for add, that's 0100. For sub, that's 0010. So that's add. Um, this is sub. So basically, these two instructions are the subsets of data processing instructions, add, sub, or, and those are all encoded in CMD. So also the shift instructions, they also have their own unique CMDs. So you can see how there's 2 to the 4. You can have basically, okay, that's 2, 4, 8, 16, 16 different data processing instructions depending on the type of CMD. What's I? So I is actually the thing that specifies. So if I equals 1, then we have immediate addressing, and say for example for a instruction that's like this, then I would be 1 because it has an immediate in it, so that means it uses immediate addressing. For instructions that are like this instead, you have I equals 0. So if it's not immediate addressing, you go down here. It's written right here. I equals 1 or I equals 0. How do you choose between register and register shifted register? So actually, for our purposes for now, the difference between register and register shifted register is actually just whenever it's a shift instruction, it's actually register shifted register. So for example, right here, we have left shift logical RD, RM, and RS. um, RS is goes here, and RM. So RM is the shifty and RS is the number of shifts. So that's why it's for shift instructions, that's register shifted register. Usually it's just a register instruction. You can also optionally shift the register stuff. Um, Additionally, for immediates, you also have a rotate here. So basically, for immediates, you have the 8-bit immediate, but actually, the final immediate that you're gonna add to the thing is actually immediate 8 shifted to the right by 2 rot. So that's rot right there. So you multiply rot by 2, and then you shift im8 to the left by that much. So you can see here that's 4 bits for rot. So rot has 4 bits, and which means its maximum is 16. If you multiply that by 2, it becomes 32. So at most, you can shift M8 by 32 places, which makes sense because and now it makes sense why we use 2 times rot, because 30 shifting something 32 times is actually going to put it back into its original place. Okay, so that's what that is. Actually, 4 bits is 15 at most, no? That's 1 um 3 this okay, this 1 3 7 15. Yes, it's 15 at most. So at most it can shift to 30. Okay. So you see an example of 2 rot later. The last thing we have that's new on this page is actually the S. So S is actually something that tells the computer to update the status registers. You've probably seen it before. So say for example, add S or sub S. The S here is the thing that tells the computer to update the status registers after this particular instruction. So the S there is the S here. So if you have S equals 1, then that means you put an S on the instruction. If there's no S on the instruction, then there's no then S is 0. So that's that. Okay, condition. As always, just to add another example of condition. So if it's LT, that's a specific condition. Add EQ. Um, that's going to be 0 0 0 0. So if you have something with no condition, that condition is 1 1 1 0. So this is the condition for always true. Okay, so next, let's look at a few examples of data processing instructions. So if source 2 is a register, so source 2 is a register. In this case, we have add R5, R6, R7. Okay, so we know that this is RD equals RN plus RM. So we know that it's register addressing. From that, we can infer that already I is 0. It's not immediate. It's an add instruction, so that's 0, 1, 0, 0. We didn't put an S, so we're not supposed to update the status registers. We put a 0 here. Okay, so Rn is R6, so we put 6 here. Rd is 5, so that's 5 here. So it's a register addressing. So this is the source 2 for register. We have 7 right here because that's Rm. Okay, so now the remaining ones, we don't have condition, so it's always true, 1 1 1 0. Opcode is for data processing instructions, 0 0. And now we're back to I. Okay, now for sub, okay, condition always true. Opcode data processing, not immediate addressing, so register addressing. Sub, so that's 0010, the CMD. You can look at the table from the ARM ISA, the ARM instruction set PDF document from the from last week. You also have you also have S here, which is 0 because you don't have you were not updating the status registers. So okay, RN is R9, RD is 8, and RM is 10. So okay, that's basically it. And if you translate that into pure binary, you get this one. Now, if you group these binaries into sets of 4, you get E0 um, 1001, which is 8 plus 1 9. You get okay, seems I was wrong about that. That's a 4. Okay, I grouped way too much over here. Anyway, you get E04, which is also the thing over here. So these are the compact way you write the machine code in terms of hex. Okay, next, immediate addressing. So let's see. There's a very particularly interesting case here, but let's see for the first case first. Add R0, R1, 42. Okay, so there's no condition, so that's always true. That's always true. Opcode is for data processing instructions. I is 1 because we have immediate addressing. Command is for add. S, we're not updating the status registers. There's no S on the instruction. Okay, so Rn is register 1. That's why that's 1. Destination register is R0. That's why that's 0. Rotation is, okay, for now 0 because 42 fits into the 8-bit immediate field. Why do we know it fits into the 8-bit immediate field? Because 42 is less than 2 to the 8, which is 256. So if it's less than 256, then that's fine. Okay. Next, sub. Okay, so now let's look at sub. Sub is the one that's interesting. Let's get the conditions out of the way. Always true. Opcode is data processing. Immediate addressing. Sub, command for sub. Don't update status registers. This first operand is R3, destination register is R2. Now you have the immediate and rotation. How did we get this from OXFF0? Okay, so let's try to write down OXFF0. FF0 would be this number. If you look at what is the largest number under 256, that's actually this number. So actually, because 256 is 100. If you can, if you can try to derive it yourself. If that's not if it sounds kind of wishy-washy to you and suspicious, you can see this is actually the binary number that's 255, so which is one less than 256. Now the thing is, the immediate that we specified right here is actually greater than 8 bits. So I mean, okay, I should have just said 8 bits. So here, 8 bits. It's already greater than 8 bits. So what the assembler did for this case is actually we took the thing that goes into 8 bits, and then we applied a rot to it in such a way that it will turn into OXFF0. So we took something that fits in 8 bits, that is OXFF, and then we applied 2 rot to it to get this. So okay, let's try. This is 255, by the way, which is this one. So since it's already 255, let's apply it to this number. Okay, so FF 0. Okay, you know what? Let's just rotate. So the full 32-bit number would be very long. Okay, it's actually going to be very long indeed. How do I do this? Um, let's try to do it in sets of 4. So let's try to do it in hex. That's 1, 2, 3, 4, 5, 6, 7, 8. So these last two are FF. So that's 255 in hex. Okay, so 2 rot equals 14 times 2, which is 28. So we need to shift 28 times. So okay, if we shift by 1 hex character, that's 4 bits. Okay, so let's rotate once. So that's FF. So that's 4, and then 8. Okay, let's just draw arrows. So that's 4, 8, 12, 16, 20, 24, 28. Okay, so with 28, we end up with OX 0, 0, 0, 0, FF 0. And this is exactly what this was. So that's what we wanted all along. So I hope that makes sense. We shifted the thing to the right, rotated, by the way, so it's not logical shift, it's rotating. We rotating shifted it to the right. Sorry, if I said left. We rotating shifted it to the right 28 times in order to arrive at this thing. So that's 4, 8, 12, 16, 20, 24, 28. One shift in hex digit is actually 4 shifts in bit. So I just did it for compactness, but you end up with the thing that you wanted to begin with. So that's how it's done here. Something to note in that case as well is if you try to write an immediate, say something like OXFF 1, this is not possible because now you cannot make this immediate out of a shift. you need to have something that's actually just 8 bits, and then you can place it in the middle of a lot of zeros. So you need to have a string that's 8 bits wide, is what I'm saying, for it to be valid for the rotation and immediate. That's the thing that we sacrifice for us to use immediate addressing. It becomes a compound instruction, I think, if you try to do something like immediate addition with this. Okay. Okay. Rot. So rot. I forgot I had this slide. So anyway, rot. So this is FF, right? So this is FF, and then we rotated it by rot. So 2 times 001 is actually 2, so we shift it to the right 2 times. So okay, that's basically that. So everything I said in the previous slide is the thing that this table is trying to show you. Okay, shifts. So this is the table that pertains to what shift does. So you can just look at that for now while I um, start drawing the left shift logical instruction. Okay, so condition always true. We didn't specify a condition. This is left shift logical without anything after it. Without anything after it also implies that S is 0. So because there's no S, we're not going to update the status register. Opcode, data processing instruction. Opcode is 00. Immediate addressing. You can see here that's an immediate. Command. Okay, command is shift instruction. So actually, the command number for shift instructions is all 1101, and it's just this. So the thing that separates the shift instructions from each other, or the thing that distinguishes them from each other, is actually SH, which is found in the SRC2 field. So that's SRC2. Okay. So here we have R0. The destination is R0. Rn is hard-coded to 0. So this thing is actually not Rn for shifts. Rn for shifts is here. So shifts become Rd, Rm, and then either Rs or some sort of immediate. So that's how shifts are written. So okay, now R9 is Rm, and then 7 is the shanty. So the shift amount. The 5-bit shift amount is Rm, and depending on the type of shift, you have here 0. So you know that it's left shift logical. Left shift logical is up here. I mean, it says 00, so we put here 00. This thing is hard coded to 0, so we're not going to touch that one. Okay, next for rotate. Okay, let's look at rotate. Always true. Opcode is data processing. Immediate addressing is a shift instruction. We're not going to update the status registers. Rn is always 0 for shift instructions. Destination register is R3. Rm is R5. And the shift amount is 21. Since it's rotate, let's look here. Rotate right is 11. So we have 11 here, or 11, 3. So rotate right is 3. So we put here 3. This thing is always 0. Okay. That's how the breakdown for the shift instructions goes. What if we're going to use registers? So now we use the register shifted register addressing mode. Okay. Left shift logical shift right. I'm sorry. Logical shift right. That's R4, R8, R6. So always true. Opcode is data processing. Immediate not addressing, so not immediate addressing, which means we put here 0. Command is shift instruction. S is 0. We're not updating stuff. We didn't say S in the instruction itself. Okay, so Rn is 0 for shift instructions. Rd is the destination, which is 4. Rs is 6. So, okay, I'm sorry. Okay, so we have Rm here and Rs here. R8, Rm is R8, so we put that there. And now it's not an immediate, it's a shift register, so we put the shift register here. And that's 6. So, but if it's shifted register, this is 0 and this is 1. So, okay, for register shifted register, you can see here it's always that one is always the seventh bit is always 0 and the fourth bit is always 1. You can compare that with this one. So actually, the fourth bit is actually the thing that tells if it's register addressing or register shifted register addressing. So if bit 4 is 1, it's register shifted register. If bit 4 is 0, it's register. So that's why in the next slide it's now 1 because it's register shifted register. Okay, LSR, logical shift right. It says here 0 1, so we put here 0 1, and that's basically it for LSR. Okay, arithmetic shift right. So always true. Opcode is data processing. Register addressing. Shift command, don't update status registers. There is no RN for shifts. Destination register is R5 stated here. RM is R1, and it's shifted by a register that is R12. So we put 12 in RS. We set bit 4 to 1. 7 is 0 for register shifted, and the shift is 1 0 because it's arithmetic shift right. So arithmetic shift right is 1 0. So we put here 1 0. Okay. Okay. So next, memory instructions. So for memory instructions, it's the same, basically yes, the same as the data processing instructions, but the func contains something different. So it's IPUBWL this time. So I'll explain what those are in the next slide, I hope. The memory instructions include these instructions. So actually forget these ones. They're also part of the okay, they're not going to be part of the single cycle data path in the next lesson, but um, they're going to be part of the instruction decoding. But basically STR and LDR, so basically store if less than or store if greater than, those are the ones that we are considering right now. Okay, so okay, we have condition as always. Opcode for memory instructions, it's 0 1. Take note of that. RN, RD, source. So source again depends on whether or not what depending on what I is. So depending on what I is, it's immediate or register addressing. And register addressing is also still again RM with some shift amount. Okay. Now I/U offset type. So the funct is made up of I P U B W L. So they correspond to specific things. They correspond to specific things. Okay. So here's the meaning of I and U. If I is 0, then it's an immediate offset. So right here. If I is 1, then it's a register offset. So right here. If U is 0, then we subtract the offset from the base. If U is 1, we add the offset to the base. So for example, we have load register, destination, let's call it RB for base. We have offset. Okay, here. So if we put negative right here, then this would be 0. Then U would be 0. But if it's If it's positive, then U would be 1 because you usually do add offset base. So that's just something to make certain operations compact. Okay, indexing mode. So okay, you can basically probably read this yourself. P and W cannot be 0 1. They have to either be 0 0, 1 0, or 1 1. So basically that basically makes things like this. So this is something implemented in order for you to do for loops easily. So you can read a memory address while at the same time writing a specific amount into a specific register. So that's what you do when you pre-index and post-index. And for pre-index, basically the address that you're reading from is R1 plus R2. For post-index, the address that you're reading is just R1, but after you read it, R1 is added, R2 is added to R1. So that's basically it. Offset is the usual way we do things. We don't change the base register. But I know this is something that's introduced to make for loops more compact in the code. So yeah, P and W specified this addressing mode. Okay, L/B operation type. So okay, STR, STRB, LDR, LDRB. So the difference between STR and STRB, this thing loads in the lower 8 bits. So these things store the lower 8 bits and load into the lower 8 bits respectively. This thing loads the entire 32-bit word. Okay. Oops. Next. Memory instructions. Okay. We already have an example of post addressing. It's great. It's 26. Okay. See here. Store. Okay. We don't have a condition, so condition is always. Opcode is memory. Okay. IPUBWL. So let's cheat and look at the cheat sheet. So if I and U are 0, I means immediate offset, U means subtract offset from base. So here. Um, okay. We're just going to derive properties from here. Immediate. Subtract. So immediate, we took that from here. Subtract, we took that from this thing. Okay. The next thing we need to know, this is post indexing. That's the way this bracket works. So the bracket is only on the base register and the offset is outside the bracket. So that's post indexing. What else? What's the missing thing? Oh, it's okay. So since it's a store instruction, L and B are 0 0. So store means L B equals 0 0. So okay, immediate means I equals, wait, what? Oh, because it's I prime. Okay, that's why. Okay, so since it's immediate and this is I prime, that's 0. Subtract U equals 0. Post index, well, you can probably tell that it's going to be 0 0 if it's post index, just because this thing is already 0 0. So okay, what a surprise, everything is 0 for this specific instruction. Okay, so Rn is 5. This is Rn destination register, but for store it's not necessarily the destination register, it's the source register. Actually, for store you have here 11, and then immediate 12, 12-bit immediate, that's 26. So actually, the im12 is an unsigned immediate because its sign turns into the U right here. So in machine code, that's what we get, and in hex, that's E405B01A. So okay, um, next, branch instructions. Okay, so I'm only eh, hmm. Okay, let's look at another load instruction first. Then, so load register, say R11 or 5. Um, let's make this pre-index um of a register. Okay, so this is base, this is offset, and now we have let's get some properties. Um, this is register addressing, pre-index, register addressing pre-index. Mm, Offset is added. So that means u equals 1. Um, Offset is added, and then it's load register, which is so start with 0, 0, 0, 1, 1, 0. Okay, so UB is 0, 1. Oh wait, no, not UB. Um, is it LB? It's LB. Okay, LB is 0, 1. Okay, so since LB is 0, 1, let's um, there's a bit too many zeros here, no? Yeah, there's one too many zeros over there. Um, okay, so let's go look at the cheat sheets. Since it's register addressed, that's 1. So I is 1, and we add offsets from base. So I and U are 1. These are this is 1, this is 1. Um, okay, so for pre-index, that's 1 and 1. So P and W are also both 1. B and L are B is 1, L is 0. Hope that's correct. B is 1 and L is, oh wait, no. L is 1 and B is 0. Okay. Okay. It makes sense why it's L is 1 and B is 0, because if it's load, then L is 1. And if there's B, then B is 1. On the contrary, if it's store, then L is 0 because it's not a load, and the absent of this B is makes it so that there's no B, which means B is 0. So um, yeah, that's L and B. I just remembered. Okay, next, branch instructions. Almost done. Okay, so these are the branch instructions that we're going to be covering. So of course they have conditions. Opcode Opcode is 1, 0 for branch instructions, and for branch instructions, that thing is always 1. So bit number 25. So bit number 25 always equals 1, and L is whether or not L is there. Okay, so you see this L? If L is there, then that L is 1. So okay, I mean you can see this. You can see that in this slide. So you have 24-bit immediate for branch target address. The upper bit is always of the 2-bit functy is always 1 for branches, and the lower bit is 1 for branch and link and 0 for B. So the presence of the L right here means this thing is 1. If there's no L, then it's 0. M24 is the number of instructions between branch target address and PC plus 8. So the branch target address, also known as the label, minus PC plus 8 equals M24. So okay, that's that one. So okay, example, branch if less than. There is a T A0 and there is here. So okay, PC plus 8 is here. So two instructions after the thing. So this is PC, right? This is PC plus 8. 80A0 is 80A8 if you add 8 to it. So that's PC plus 8. And now you have there over there. So 1, 2, 3. You have M24 has to be 3 for this code. So if you translate BLT there, M24 will be 3. Condition always, because there's no condition for BLT. Okay, never mind. It's branch if less than. Okay. So the condition code for branch if less than. So okay, it's BLT. So don't get confused now. The LT here does the L here doesn't mean it's a branch and link. The L here means it's connected to LT, which means it's the condition for the branch. So BLT branch if less than condition right here. So what if branch and link if less than, then that's BLLT. Okay. So condition is 1011, that's less than. Opcode 10, because it's a branch instruction. Funct, okay, that's 10. 25 is always 1, 24 is 0 because it's not a branch and link. M24 is 3, we've already seen that. So, okay, that's basically it for that one. Branch and link, okay. Branch and link difference is bit 24 is 1. So since it's branch and link, yes, bit24 is 1. Condition always. So we said BL test. So we didn't specify a condition code here. It's just a BL. So condition is always true. 1110. Opcode for branch instructions. Funct is but okay, bit25 is always 1. In 24 is minus 6. So let's try to see how that came to be. Branch and link test. So this is PC. PC plus 8 is over here. And let's count. 1, 2, 3, 4, 5, 6. 6. But backward. So 6 upward is negative 6. So that's negative 6. Yay! Okay. So this is the summary of addressing modes that we have. Basically, this is used for branches if it's PC relative. Base is used for memories. So base plus so if base plus offset where the offset is immediate, base plus offset where the offset comes from a register, or from when the offset comes from a immediate shifted register. So we didn't exactly cover this, but you can probably think of how this works because you have a shanty right here, or rather here. So this is for immediates. This is for memory instructions. You have a shanty here. Basically, this thing just becomes a shanty over there. Okay, so these ones are for data processing instructions. So, okay. Okay. See you in the next lecture.